All right, let's get into it. Today, we're going to peel back the curtain on a pretty simple-looking basketball game. We're going to uncover the really elegant code and math that takes a simple swipe of your finger and turns it into a perfect swish. So, have you ever actually wondered how that works? You swipe your finger, and the ball flies in this perfect arc. Well, it's not magic. It's all math and logic. We're going to follow the complete journey of one single shot. From the second your finger hits the screen, through all the physics of its flight, right up to that satisfying swish as it drops through the net. And here it is, the entire game loop in a nutshell. It all boils down to these 5 key steps. First, the game captures your drag. Then, it converts that into power and direction. Third, it applies that to the ball as a physical impulse. Fourth, it figures out if you scored or missed. And finally, it updates the screen. We're going to break down every single one of these. Now, behind the scenes, there are 3 main scripts making all this happen. You've got the GameManager, which is kind of like the brain of the operation, keeping score and all that. You've got the score gate trigger, which is like the referee, just watching the hoop. But the real star of our show, the one we're going to focus on, is BallThrower.cs. That's where all the magic of turning a swipe into a shot really happens. So, let's start at the very beginning. How does the game even know what you're trying to do? It all starts with capturing your intent, translating the movement of your finger into data the computer can actually understand. The game tracks 2 really simple points, where you first touch the screen and where you lift your finger up. Then, by subtracting the start point from the end point, a process called vector subtraction, the game creates this sort of virtual arrow, and that arrow tells it everything it needs to know, both the direction and the distance of your swipe. And believe it or not, it all comes down to this single, elegant line of code. It just takes your current drag position and subtracts the position where you started. The result is what we call a swipe vector. It's a single piece of data that holds both the direction and the length of your swipe. Pretty cool, huh? Okay, so we've got our swipe vector, but that's just a simple line on a 2D screen. How does the game turn that into a powerful 3-dimensional basketball shot? Well, this is where the math starts to get really interesting. First off, the game needs a consistent way to measure the strength of your swipe. I mean, think about it. A 100-pixel drag on a tiny phone screen should feel the same as one on a giant tablet, right? So it uses a process called normalization. It takes the raw length of your swipe and scales it down to a universal value that's always between 0 and 1. And here's the code that pulls it off. It takes the length of the swipe, that's its magnitude, and it divides it by a maximum value that the developer sets, let's say 350 pixels. So a full 350-pixel swipe gives you a strength of 1. A 175-pixel swipe gives you 0.5. Makes sense, right? And that clamp 01 function, that just makes sure the strength can never go above 1, no matter how wild your swipe gets. So if you were to write it out as a simple math formula, this is what it looks like. Your swipe strength is just the ratio of your swipe's length to the maximum possible length, and it's always capped at 1. It's a really clean and effective way to measure how hard you want to throw the ball. Okay, so we have this strength value from 0 to 1, but what does that actually mean in the game's physics? To figure that out, we use a super handy function called linear interpolation, or just Lerp. It's a way to translate that 0 to 1 value into an actual shot power, fitting it perfectly between a minimum and a maximum power that the developers have set. This line of code is basically saying, hey, based on our 0 to 1 swipe strength, find me the matching value between min power and max power. So, for example, if the minimum power is 10 and the max is 18, a half-strength swipe of 0.5 will give you a power of 14, exactly halfway between them. Now for the direction, and honestly, this is the really clever part. The game, for the most part, completely ignores the left-right direction of your swipe. Instead, it creates its own perfect aim, a kind of pure direction pointer from the ball straight to the hoop. And it does this using what's called a unit vector. So this line of code first calculates the vector, the arrow, pointing from the ball to the hoop. But then it does this crucial step, .normalized. That little command strips away all the distance information, and it scales the vector's length down to exactly 1. All that's left is a pure direction, pointing perfectly at our target. Of course, a straight line to the hoop isn't a real basketball shot, right? That's more like a laser beam. To get that beautiful, satisfying arc, the game uses another really simple math concept, vector addition. Just look at how simple this is. The code takes our straight line vector, that's pointing to the ring,
and it literally just adds an upward vector to it. By combining forward and up, we get a brand new direction that points up and towards the hoop, and that's what creates that perfect parabolic arc. But here's something that's really cool. The game doesn't just calculate this arc when you shoot, it actually shows it to you before you even release your finger. So how does it predict the future? It uses one of the most famous equations in all of physics, the projectile motion formula. You might even remember it from high school. This equation can perfectly predict the position of any object that's just moving under the force of gravity at any point in time. And there it is, that exact formula just translated into code. Now, the game doesn't just solve this once. It runs this calculation in a super fast loop, predicting the ball's position at dozens of tiny little time steps into the future. And then it just plots all those points on the screen to draw that smooth, predictive curve that you see. Okay, so we've thrown the ball, its arc is perfect, but how does the game know if it was a swish or a brick? It turns out it's not quite as simple as just checking if the ball touches the hoop. It actually uses a really clever two-trigger system. You can think of them like invisible laser gates. There's one at the very top of the hoop and another one at the bottom. To count as a valid score, the ball must pass through that top trigger first. Only then, if it passes through the bottom trigger, is the score awarded. This makes sure that only clean shots that actually go through the hoop from above are counted. It's really important to get that all of these numbers, the power, the arc, the sensitivity, they aren't just random. They're part of a really delicate balancing act. Developers treat these values like dials in a tuning lab. They're constantly tweaking max power to stop you from overshooting, adjusting the upward boost to create a satisfying arc, and changing max drag pixels to get the swipe sensitivity to feel just right. It's all about finding that perfect game feel. And this right here is really the core design philosophy of the whole game. The math is intentionally designed to handle the difficult part, the aiming, for you. By always pointing the shot toward the hoop, it frees you up, the player, to focus on the two things that feel the most fun, getting the power and the arc just right. You know, this whole system is a fantastic foundation for a simple, really fun game, but it also leaves us with a fun little question to think about. If you wanted to give the player more control, how would you change this math? How could you start to incorporate the horizontal part of their swipe to let them aim left or right? That's the beauty of code and game design. There's always another layer of complexity you can add,